And Lucas, you're on.
Oh, put on the spot, but yo, we're back. Section 4.4, indeterminate forms and La Hospital's rules.
La Hospital.
With Mr. Laverick and company.
And company. Very good. Thank you. Hey, everybody. Actually, is everybody here today?
Yep.
Yeah, so no one will be watching this video. That's okay. We talked about, yesterday we talked about indeterminate forms, which are basically ones that if you're trying to find the limit, it's not able to be found easily. You know, maybe you've got a 0 over 0, or you've got an infinite over infinite, you've got a negative infinity over negative infinity. Whatever it may be, it's an indeterminate form. Okay. You know, we studied, we looked at right at the beginning, ln of x over x minus 1. ln of x over x minus 1 as the limit approaches 1. You know, if I plug in 1 into ln of x, that would be ln of 1 would end up being 0. Right? ln of 1 would end up being 0. And then 1 minus 1 in the denominator would end up being 0 as well. So I get this indeterminate form is 0 over 0. Another indeterminate form would be if you've got something infinite over infinite, right? Infinity over negative infinity over negative infinity. So what do we do with those things? There's a thing called L'Hopital's rule. Suppose that f and g are differentiable and g prime is not 0 as long as the derivative of the bottom is not 0. In an open interval I that contains a, except possibly at a, because we're just doing a limit. We don't really care what happens at that point, just near it. Suppose that the limit of f of x is equal to 0 and the limit of g of x is equal to 0. So the top goes to 0, the bottom goes to 0. Or the top goes to positive or negative infinity, and the bottom also goes to positive or negative infinity. In other words, we would have an indeterminate limit. That's what that means. If the top and the bottom go to 0 over 0 or the to infinity over infinity, then you know that the limit as x approaches a of f of x over g of x is actually equal to the limit as x approaches a of f prime over g prime. And we talked yesterday about how it's really nice when we can reduce those functions on top and bottom down a little bit, because it might make them a little bit more easy to work with. Just make sure that the premise, like the hypothesis, is fulfilled, right? You can't do L'Hopital's rule if it's not indeterminate, right? It's got to be indeterminate for you to be able to do L'Hopital's rule. All right, so let's get to an example here. If you print out the notes, I screen captured a new one in. Let's do this one, shall we? It's very similar to the one that we captured in yesterday. Who stole them? Lucas? Sorry. You know, in high school, I was sitting in the study hall with my friend, and some guy bet him that he wouldn't eat his hat. And guess what he did? He ate his hat. No. He ate his whole hat. All except for like the plastic part in the brim.
Did he cut it into pieces?
Yeah. No. He said, I bet you want to eat your whole hat. He said, I would, but for a price. He said, okay, $50.
Did he do it like right there in like that 40 minutes?
So he like got scissors out and would cut up his hat and ate his hat. In study hall one day. The things people do for money. Anyway, we got x to the third minus 7x squared plus 10x over x squared plus x minus 6. Now, if I tried to plug in 2, if I tried to just do direct substitution, what happens to the numerator? Well, I would get, you know, and what am I saying here? I'm saying, what happens if I try to evaluate this limit? The limit as x goes to 2 of x to the third minus 7x squared plus 10x. Well, that I could just do direct substitution because that's a polynomial. So that would be 2 to the third minus 7 times 2 squared plus 10 times 2. So 8 minus 28 plus 20. What happens? 0. Okay, so the limit of the top is 0. The limit of the bottom, as x approaches 2, of x squared plus x minus 6. Well, that would be 2 squared plus 2 minus 6, which is 0. So we know that L'Hopital's rule, the hypothesis, is fulfilled. So now we can apply it. We say that the limit as x approaches 2 of this is actually equivalent to the limit as x approaches 2 of the derivative, which in this case is 3x squared minus 14x plus 10, all divided by 2x plus 1. Follow me there? Now, can I plug in 2 at this point? Yes. And that's why L'Hopital's rule is nice, because usually when you take the derivative, you'll be able to do direct substitution at that point. So 3 times 2 squared minus 14 times 2 plus 10, all divided by 2 times 2 plus 1. All right, so we can do this in calculators. 4 times 3 is 12 minus 28 plus 10 all over 5. So what would that be? Negative 16, so negative 6 fifths. Is that what you guys got? Yep. Just trust you again. Blindly believe whatever you say. Negative 6 fifths. So that's really L'Hopital's rule in a nutshell. Making sure that it fits the hypothesis. And if it fits the hypothesis, then you can use the derivative on top of bottom. Yeah.
Does the answer, like, limit as x approaches 2 equals negative 6 fifths, or is it just negative 6 fifths?
Well, you could say here at the beginning. See, what's useful is the limit as x approaches 2 of the derivatives is equal to that. So therefore, we could go back to the beginning and say the limit of just the 2 functions is negative 6 fifths.
Okay.
Does that make sense?
Yeah.
The answer really is negative 6 fifths. But the cool part about this is that we can bypass having the need to do any of that stuff with the original functions. We can just say it's negative 6 fifths is the derivative. Go to that.
What was like the question at the end of that? Like what were we solving for?
We're solving for the limit. We're finding the value as x approaches 2 of this wacky rational function. You know, if you plugged it in your calculator and saw, okay, what's happening at 2, you know, it probably, because I plug it in and the denominator is equal to 0, it's probably a vertical asymptote. So we'd have to see what's happening on either side. Well, it looks like it's approaching 2. It's either a vertical asymptote or a hole.
We get the derivative of 5
Yeah, and that's L'Hopital's rule. It says that if the top and the bottom both either go to 0 or infinity, then you can find the derivative of the top and the bottom. And the limit of this is actually equal to the limit of the derivative. And then so you just find that. And usually it's easier because derivatives are usually simplified.
We could do that for that and like simplify those.
Right. Like what we talked about yesterday at the very beginning was that, you know, there are times when we could cancel things out to find limits, right? That was an easier case where, you know, we could cancel things out to find limits. Like this is an indeterminate limit right here, right? We could use L'Hopital's rule to find that if we wanted to. And actually, in my opinion, if I know it's indeterminate, it's easier to use L'Hopital's rule because look, you would just say 2x minus 1 over 2x and then plug it in. 2x minus 1, if when I plug in 1, 2 times 1 minus 1 is 1 over 2x. 1 times 2 is 2, 1 over 2. And I can jump straight to my answer. I don't even need to go through this process of factoring, canceling, and then put. Okay, so let's do another example. I didn't save my notes from yesterday, so we'll have to tell me which ones I did.
Number 4.
We did we do this one?
Yeah.
Did we do?
Yeah.
Oh yeah, don't remind me. And then this, I captured that one in this one, right?
Yeah.
This is where we were at. I want to do a trig one. There are some trig ones in your homework too. And on this one. I did make the test. I've yet to make the review, but I did make the test, so that's done. Now I'm going to try to, yeah. Say that again?
When's the homework?
I'm going to make it tomorrow night. Hopefully we finished it. Honestly, we've essentially finished the notes already. Now we're just keep doing examples. Yeah. and just seeing how it applies to certain things. Like this. Is this an indeterminate limit? It's always good to make sure to see, is this an indeterminate? So the limit as x approaches 0 of tangent of x minus x is, what is that? Well, if I go to try to plug that in, tangent of 0 minus 0. What is tangent of 0? What is tangent of 0? Well, what is tangent? Y over x, sine over cosine, right? Okay, what's the coordinate out here at 0? 1 comma 0. What's 0 over 1? 0. So this is all equaling 0 minus 0 is 0. Okay, and then we would say, okay, don't need to cross my L. The limit as x goes to 0 of x to the third is also 0, right? Because I just plug it in. So this is an indeterminate limit of the form 0 over 0. Okay, now, here's the hard part about this. We got to figure out those derivatives. Limit as x approaches 0 of, and we got to find the derivative. Well, let's do the easy one first. The bottom's pretty easy, right? Again, you don't have to use the quotient rule. Unless there was a quotient in the numerator and or the denominator, obviously. Then you would have to use the quotient rule. But, don't be tempted to use the quotient rule because you see a fraction. You're just going to take the derivative of the top divided by the derivative of the bottom. All right, what's the derivative of tangent? Cheat sheet.
Secant squared.
Secant squared. Did you know that off the...
Yeah, I did.
Did you really?
Yeah, do I get candy?
Let's go. I don't have any candy. You get a high five.
Can you guys venture past and get me lunch?
Get your, like, phone it in.
Yeah.
Hey, can I get a, I don't know.
Mac and cheese.
Mac and cheese. Really?
What I'm feeling right now.
Secant squared x minus 1. Okay, now, I would now see if I could possibly plug this in. Can I? Like, think about this. The limit as x goes to infinity of secant squared x minus 1. Well, secant squared of 0, you can trust me on this one. Secant squared of 0 is 1, minus 1 would be 0. And the limit as x goes to 0 of 3x squared is also 0. So this is another indeterminate form. This is another indeterminate form. So we keep using L'Hopital's rule. Okay, so this gets a little bit more difficult. Okay, we want to find the limit as x goes to 0 of, okay, we got to find the derivative of secant squared. The derivative of secant squared is, well, the derivative of secant is secant x tangent x. Yeah, 2 secant squared x tangent x. Ooh, nice. So it's 2 secant squared x tangent x. Why is that the case? Because remember, secant is, secant x squared is secant squared x, right? That's the notation there. So this is technically a chain, right? This is technically a chain rule. So it would be the derivative of secant squared would be 2 times secant x, 2 times secant x, and then find the derivative of secant x, which is secant x tangent x. So if I wanted to write it out, it would be 2 secant tangent, which is 2 secant squared tangent. Can we just skip this? Oh, I thought you meant like this section or something. Yeah, we need to stop. That's from the derivative of secant. The the derivative of secant is secant x tangent x. It might be a good idea to refresh some of those derivative rules. Yeah, but we can reduce it before we do that. Watch what we could do here. First off, what can we reduce? Yeah, 1/3, right? Now, remember what we talked about at the beginning of the year with limits. If there's a constant within the limit, can't I pull that out in front of the limit? Yes, I can do that. So we would see that this would be, that'll reduce it to a 1/3, right? So what I can really do is take 1/3 times the limit as x goes to 0 of secant squared x tangent x over x. And now I'm going to reduce it down a little bit even more to say 1/3 the limit of x going to 0 of secant squared x times the limit as x goes to 0 of tangent of x over x.
How come that one doesn't get the 1/3?
It's all multiplication. They're both getting the 1/3. Because I can break it apart. I can evaluate the limits separately. All I did was just break apart this fraction. I took the secant separately from the tangent x over x.
You have to put the 1/3 on both of them.
No, because that's what she asked. It's all multiplication, so it doesn't matter. It's not like we need to distribute it or anything. Because there's no plus or minus. It's all multiplication. Now the nice thing is what is secant? Like, can I evaluate this? Right? What is secant of 0? Isn't it 1 over cosine? Right? So 1 over cosine of 0. 1. Right? So what's this going to go to? 1. So it's really just going to be 1/3 times 1 times the limit as x goes to 0 of tangent of x over x. Yeah, Tom. Because it's multiplying, it's not adding or subtracting, so I don't have to split apart the denominator. I only need to do it to one of them.
Okay, so in that case, would you choose which one you wanted to?
Right, but I don't want to do it to secant because I can evaluate that. I can actually take this and figure out that it is 1. Because what is this still? That's still indeterminate. Okay? This is still indeterminate because I'm going to get another 0 over 0. Well, the nice thing is that their derivatives are quite easy again. Times the limit as x goes to 0 of, well, the derivative of tangent, that's again secant squared. Secant squared? No, just, yeah, it's secant squared. Sorry, I had it right. Secant squared x over 1. Well, secant squared, we just evaluated it. 1 over cosine was 1. So this is going to be 1/3 times 1 over 1. No, that's just in this case that it happened to be 1/3 times 1. It could have been like 1/3. Could have ended up being like 1/3 times 0. Or 1/3 times infinity. Then it would have been infinity. So what did we learn on this one? A, to brush up on our derivatives.
I'm good.
And B, yeah. And B, to keep doing L'Hopital's rule until you get something that's reduced enough that you can find it.
Are there any point where will go on forever.
Yeah, I think it's.
Yeah, that's what I was very, I mean, I don't know if it's possible to do that. I would hope not.
Like,
I would never
would
get
go
used to
off,
something.
if that would be possible.
What's that?
Is there gonna be a question like this on tests?
I mean, I don't know if it's gonna be this difficult, but I wanted to show you something. I wanted you guys to practice finding limits of trig, or finding derivatives of trig, and also remind you guys of like the algebraic properties of limits. Like you can pull a number out if you wanted to. If it's a constant, you can multiply that constant out. You can, if it's a product, you can separate the limit into those products, right? You can do all those algebraic things with limits if you need to, if it's possible to. Does that make sense?
Yeah.
I know I didn't really answer your question specifically, but I would consider this a more difficult problem than what I would put on the test.
Okay. So there won't be one that's.
Good exercise, good mental calisthenics, but. Yeah. Let's take a look at this one. Yeah, it's quick. Honestly, I was surprised with how quick this one went. Yeah, and I write out. I work slow.
You also have to recognize, we're not a code. So, it might very well take us a little bit.
Okay. So, let me ask you something. If I wanted to go and use L'Hopital's rule, I would say the limit as x goes to pi from the negative direction, and then we would find the derivative of the top and the derivative of the bottom, right? We would say, what's the derivative of sine? Just cosine, right? Just cosine.
Were you there yourself?
I was. Everybody said negative cosine. I was like, good thing I have my cheat sheet right here. It's cosine over, okay, 1 goes away, and then it's negative cosine, right? So positive sine. So it's tangent, right? Wait,
No, it's
cotangent.
Yeah, that's what
Yeah, Claire? Okay, what is cotangent of pi? Well, it's 1 over tangent of pi. Okay, I wanted to show you this. So this is undefined, right? This is undefined. And it's not necessarily an indeterminate form, because what is cosine of pi? -1, right? If I try to do direct substitution, and then what is sine of pi? 0. So is this truly an indeterminate form? No, it's not 0 over 0, it's -1 over 0. So what happened? What is going, how, did we check the hypothesis? No. We should have checked the hypothesis. And here's why. If I take the limit as x goes to pi of sine, oh, what is that? What is the limit as x goes to pi of sine? It's 0. But what is the limit as x goes to pi? I know from the negative. Of 1 minus cosine. Wait a second. No, it's -1. 1 minus -1. It's 2. It's not 0, it's 2. Yeah? I'm going to pi, right? I'm going on the right, so it's -1 for my x value, right? So is this even an indeterminate limit at the very, very beginning? No. So I can actually just evaluate this. This would have been 0/2 or just 0. See, I didn't check the hypothesis. And when you don't check the hypothesis and it would have worked, you get something funky when you try to use L'Hopital's rule. You get something that's wrong when you do L'Hopital's rule. Okay, you've got to check the hypothesis to make sure that it's going to be an indeterminate limit. You guys freaked me out there. I was like, you guys all said 0, and I was like, wait a second, no, it shouldn't be 0. Yeah.
Will there be a question like this?
I don't know. I mean, I guess I could give this. Yeah,
You're gonna make us check it.
I'm gonna make you check. Yeah, you should always assume to try to check it to see if this you can possibly do L'Hopital's rule. Yeah.
If it did work, and I don't know if we're gonna do an example like this, but does the to the left mean anything like the pie to the left?
We just have to be careful when we're going to the left from the negative direction. I think they just have to do that on there because it would be like an infinite one.
Okay, so it
Yeah.
doesn't like change the way.
Not in this case. Not in this case.
But if if it wasn't coming from the left, then it would have been 0, right?
If it's coming from the left.
Well, you know, what if that negative wasn't there?
We would say, I'm not sure that it does anything. Sine of x, let's take a look at this, hold on. This is a good thing to do. Sine of x divided by 1 minus cosine of x. Let's see if we can tell by the graph. Does it matter? I don't think it matters in this one.
When would it matter? How?
I think it would have mattered like down here. Like if we had tried to use L'Hopital's rule, because you know how it was divided by 0? Yeah, that's why. Because watch here, if I plug in y equals cotangent of x, I think they were getting you to try to work a little bit more down here. Right, 1 over tangent of x. Right, which is 1 over tangent.
Gotcha.
Because if I graph that, they wanted to say, looking at the graph of cotangent, looks like 3.14. From the left side, where is this going? To negative infinity, right? So they were trying to get you to do a little bit more work, to graph it and to see, okay, from the left side on the graph of cotangent at pi, so saying like right there, applying L'Hopital's rule would have wanted you to think this was going to go to negative infinity. But that's not actually the case because L'Hopital's rule never actually came to play anyway, because it wasn't an indeterminate limit. That's why they put to the negative. Because if they would have put just going to pi, does the limit actually exist? No, because it's going up on one side and down on the other, which means the limit does not exist. There are other indeterminate forms. There are things called indeterminate products, and this is basically you could, turn indeterminate products into indeterminate quotients to use L'Hopital's rule. Because if you just take 1 over that thing, you can turn it into, like, if you've got f times g, and this is indeterminate, what you could do to turn it into something you could use for L'Hopital's rule is like f times 1 over g. Or if you wanted to make it g times 1 over f, because those are equivalent, right? If you have f times g, you could really make that f times 1 over g. So if you had a product that was indeterminate, you could turn it into something that you could use L'Hopital's rule with by making it a fraction. In other words, you could also say that if I've got f times g, you could make that g divided by 1 over f. You could manipulate it a little bit so that you can use L'Hopital's rule. Like for example here, if you've got the limit as x goes to 0 from the positive direction of x ln of x. See, I can't use L'Hopital's rule here because I don't have a fraction, right? But if I try to take 0, this going to 0, and then this, well, what happens when I try to take the limit as x goes to 0 of ln of x? Can I plug that in directly? Think about the graph of ln of x. Looking at it from going from the positive direction, what is the limit? Negative infinity, right? So this is actually 0 times negative infinity if I tried to directly substitute. So this is an indeterminate limit. This is one that I can't actually find algebraically. So what I can do to use L'Hopital's rule is turn one of those things into a reciprocal to make it a fraction. Like for example here, let's not worry about ln of x. Let's not try to turn ln of x into a fraction. Let's just turn x into a fraction. Leave ln of x on top and make this 1 over x. Because isn't that equivalent to saying x times ln of x? Right? I'm just algebraically manipulating it so that I can use L'Hopital's rule. Okay. So when I go to do that, and this is an indeterminate limit, right? If I go to find this, it's negative infinity. If I go to find this, it's negative infinity, or it's infinity. So I know these are both infinite over infinite. I can use L'Hopital's rule here. I would then say the limit as x goes to 0 from the positive is 1 over x, because that's the derivative of ln of x, divided by the derivative of 1 over x. But isn't 1 over x just x to the negative 1? Right? So I'm going to say negative 1 x to the negative 2. Right? Bring the negative 1 down front, reduce the exponent by a factor of 1. Okay, well that's like saying 1 over x divided by negative 1 times x to the negative second, right? Which is another way to say 1 over x divided by, okay, evaluating this, negative 1 over x to the positive second. You follow me there? All I do is just turn that negative exponent into a positive exponent by putting it into the denominator. Keep change flip. Over negative 1, but that doesn't really matter, does it? So algebraically, this will reduce down into just what? Negative x. Okay, so which means I need to find the limit as x goes to 0 from the positive of negative x. Well, direct substitution, negative 0. So what I can say there is this product actually goes to 0. Okay, that's like the final statement, is that limit actually equals 0. And how did we do that? Well, we turned that product into a quotient. We turned it into a quotient so that we could evaluate it. Okay.
I only do it once. Yeah.
Quotient. You could do also differences if they can combine together to be a quotient. Like I could do this example tomorrow if we'd like, but can't I find common denominators and make it one big fraction, and then potentially use L'Hopital's rule if I wanted to, if it worked, right? If it did the hypotheses, right? Okay. So, moral of the story with those last couple of slides is that you could possibly turn things into fractions. Okay, you could possibly turn things into fractions so that you could eventually use L'Hopital's rule. Yeah.
Can you go back to the slide 11?
This one?
Mr. Lovett.
Hold on just a minute. Yeah. Are you good? Okay, yeah.
Face restroom.
Yeah, go for it. Yeah. I'm going to turn off the, hold on one sec, Claire. I'm going to turn off the,
I'm good.
You're good? Okay.